Elements are found everywhere. In the soil, in that tree, in bugs, the air, even way up in space. You see, everything is made of elements. Elements are the simplest forms of matter. They join together to form compounds which make up everything. In order to better understand the world around us, scientists keep track of all known elements on a chart called the periodic table. Hello, I'm Misty Demery. Welcome to Biosphere 2. Biosphere 2 is a man-made environment that consists of 5 different biomes or ecological communities. Biologists classify the organisms found in each biome by their similar characteristics. For example, if we were to go over to the coral reef biome, we would find algae and organisms that need salt water to survive. They may be very different from each other, but they all share some similarities. Organisms in the desert biome have characteristics that allow them to live with very little water and high temperatures. These are their similar characteristics. In much the same way, chemists classify the elements by their similar properties. The gases that make up this atmosphere and the metals in this soil are listed on the periodic table. Today, we're going to study the organization of the periodic table and some of the elements. By the end of this program, you'll be able to interpret the atomic structure of every element on the table. You will also be able to describe the properties of an element by its position on the table, and you will become familiar with many of the elements and where they appear in our world. Pretty impressive, huh? It's not that difficult. In fact, it'll be fun. Let's get started with a little history. During the 1860s, several European scientists were attempting to categorize the elements. An early version of the periodic table was created by Dmitry Mendeleev, a Russian chemist. The chemical symbols that Mendeleev used, the 1 or 2 letters that represent the elements, are still used today. Some are obviously the initial letter or letters in the full name. Others don't seem to match the name. For instance, the symbol for potassium is K and sodium is Na. These symbols actually come from their Latin names, kalium and natrium. This is the case for many elements. Silver and tin are 2 more examples. Symbols make it easy to write chemical equations. Mendeleev listed the known elements, about 70 at the time, in columns according to their similar properties, and then arranged the columns in order of their atomic mass. He noticed periodic recurrences or patterns. According to the patterns, Mendeleev marked spaces in his tables where he believed additional elements belonged. Gradually, these new elements were discovered and they fit the descriptions he had predicted. A short time after Mendeleev's death, a young British chemist named Henry Moseley improved the periodic table. He determined each element's atomic number by testing its nuclear charge. By this time, it was determined that protons have a positive charge and electrons have a negative charge. The atomic number is the number of protons each atom of an element has. Let's look at an element that you can find quite a bit of in the rainforest's lush soil: carbon. Every atom of carbon has 6 protons. If an atom has more or less than 6, it is a different element. So Moseley arranged the elements in order of atomic number rather than atomic mass. This is how the periodic table is arranged today. Of course, many elements have been discovered and added since then. Some scientists have even designed their own models, but the information is basically the same. Moseley's table wasn't too different from Mendeleev's. If you look at the atomic mass numbers on the periodic table, you'll find that they increase in the same order as the atomic number. There is a fairly simple explanation for that pattern. Atomic mass is the sum of the mass of an atom's measurable parts, the protons and neutrons. Each one equals 1 atomic mass unit. Electrons are important subatomic particles, but they don't weigh enough to count in the mass number. As the number of protons increase from one element to the next, so does the atomic mass. Another pattern you might notice is that the atomic mass is usually around double the atomic number. That's because the number of neutrons in each atom is usually the same as or similar to the number of protons, making the atomic mass about double the atomic number. Sometimes the mass is more than double. Take the element iridium. Iridium's atomic mass is 192.217, almost triple its atomic number of 77. Unlike protons, the number of neutrons can differ among atoms of the same element. Atoms with different numbers of neutrons are called isotopes of an element. An element that is in the atmosphere around us is hydrogen. Hydrogen has 3 isotopes. Protium has no neutrons, deuterium has 1, and tritium has 2. Of course, they all have 1 proton, but the difference in neutrons gives these isotopes different atomic masses. So, which atomic mass do you think is listed on the periodic table? Let's see. Hydrogen has an atomic mass of 1.0079. That's because the atomic mass is a weighted average. A weighted average represents the amount of each isotope occurring in nature. 1.0079 is just a tad over 1. So that tells us most of the hydrogen that exists is protium, with a very little bit of the heavier deuterium and tritium. So the atomic number of each element determines whether an element lies on the periodic table, and the atomic mass follows suit. But there is one more very important pattern to cover: the electron levels. Although electrons do not weigh in on the atomic number or atomic mass, their numbers increase in sync with the protons. Electrons orbit the nucleus in energy levels. The maximum number of electrons in each level is standardized. These levels fill up in a pattern which corresponds with the organization of the table. This pattern plays a huge role in the chemical and physical properties of the elements. Let's look at magnesium. Its first electron level holds 2, the second holds 8, and the outer level holds 2 electrons. The electrons in the outer level are called valence electrons. Magnesium easily combines with other elements and gives up its valence electrons. As a compound, it helps leaves survive. Now, as we know, everything in this place is a combination of elements. Elements form compounds in 2 ways. Sharing valence electrons is called covalent bonding. The water molecule is a good example. Some elements form bonds by transferring electrons. These are called ionic bonds. By giving up and taking extra electrons, atoms become electrically charged, or ions. The transfer creates oppositely charged ions that are attracted to each other. On the periodic table, the valence number increases by 1 for each element moving to the right. This pattern affects the way elements combine with other elements. It's amazing how a pattern of such microscopic proportion can affect the combination of elements and compounds in nature, in organisms, in non-living materials, and in our atmosphere. Mendeleev originally created the periodic table because he wanted to track these patterns. The rows running horizontally on the periodic table are called periods. As you can see, there are 7 rows or periods. With the exception of hydrogen, the first element in each period is a very active solid. Look at lithium. It is the first element in period 2. Lithium is one of the most active elements on the table, causing quite a bit of heat. Its 1 electron in the outer shell causes it to readily mix with the other elements. As you move across each row, the elements are less active and less solid. At the right end of period 2 is neon, a noble gas. Its outer level of electrons is full with 8, which keeps it from naturally combining with other elements. Back to the left side of the table, we can see that each new period starts a new energy level of electrons, which fills as the period progresses to the right. The periodic table is also classified by the 18 vertical columns, which are called groups or families. Most periodic tables show two sets of numbers for the groups. Columns 1, 2, and 13 through 17 are also numbered 1 through 7a, while groups 3 through 12 are numbered 1 through 8b. The A groups are called representative elements because they represent the whole spectrum of elements from metals to nonmetals. In each A column, every element has the same number of valence electrons. In fact, the number of valence electrons for each A group matches its group number, which increases by 1 as we move across the table to the right. The B groups don't follow that same pattern. Groups 1b through 8b are called transition metals. Their outer shells have 1 or 2 electrons, except for palladium. Transition metals are actually organized by the number of electrons in the second to last energy level, called the penultimate level. As you get deeper into chemistry, you will study sublevels of electrons, and the distinctions between these two major groups will make more sense. For now, let's apply what we've learned about these patterns to the different categories of elements. As we examine the categories, we will begin to see that some elements occur naturally and others are only found in compounds. Their chemical and physical properties determine why certain substances are found more readily in certain environments than others. So,